Hello dear viewers, I am Khan Bahadur, Assistant Professor of Statistics, and you are watching a video from my YouTube channel Statistics by Khan. Dear viewers, I hope all of you will be doing great. Dear viewers, this YouTube channel Statistics by Khan has been created for basic statistics with a view to help the beginner students of statistics, the researchers of all fields, and other learners of basic statistics. I have also a Facebook page and group with the same name, Statistics by Khan. You can visit them for steps related to basic statistics. Dear viewers, for better understanding of concepts in my video, I would recommend you to watch the full video. After watching the full video, I assure you, you will understand the concepts very clearly. In today's lecture, we are deriving the general statement for the confidence interval of the normal population mean. So today's lecture is very much important, and I will try to explain very technical things in this lecture. So from my point of view, this would be an important lecture especially for the statistician. So let's start the lecture. Confidence interval for the mean of normal population. What does it mean? It means that an interval that is constituted by two limits and where the population parameter mean is expected to lie within these two limits, and with this interval some level of confidence has been attached. So such interval is called confidence interval for the mean of normal population. What does it mean? Suppose we have a normal population and its mean is unknown. So then what we are doing? We are constructing a confidence interval, and in that interval the mean of the normal population is expected to lie, and with that interval we are attaching some level of confidence, as these have already been discussed in the last lecture. That is estimation by confidence interval. We have discussed the things in that lecture. So now we are deriving the general statement for the confidence interval of normal population mean. For the construction of confidence interval for the mean of normal population, what is needed? Suppose we have a normal population that contains x1, x2, x3 up to xn, but this n is capital to differentiate it from sample observations. If xn is capital, it means the observations are population observations. If this n is small, so it represents the sample data. So we are differentiating with this notation. We differentiate sample data and population data. Okay, is the population units. Then this population would have mean that can be denoted by mu. As we have assumed this population is normal, so it must have a mean. So that mean can be denoted by mu, and it would also have a standard deviation that can be denoted by sigma. Each population is having its mean, its variance, its skewness and kurtosis. But for the normal population, we need only these two. The mean and the variance are standard deviation. So that is why we have shown only the mean and the variance. Okay, so these are the units of normal population. And these units may be having a population mean and a population standard deviation. What do we next assume? Let the population mean mu is unknown and the population standard deviation sigma is known. And hence we are estimating the population mean. So as we are constructing confidence interval for the mean of normal population, so that is why the population mean must be unknown. So in that case we can construct a confidence interval for it. So as the population mean is unknown and standard deviation is known, so what we will do next? We will take a sample from this population. Now for the estimation of population mean, we are taking a sample from the above normal population in order to estimate the unknown population mean. The sample units can be represented as x1, x2, x3 up to xn. But this time xn, this subscript n is small n, it is not capital N. So this is the differentiation between the population general observations and the sample general observation. Now, if the mean is computed from this sample, then this will be called a sample mean and will be denoted by x bar. Further, we know that the mean of x bar is mu and the standard error of x bar is sigma over under the root n. So these are facts, and on the basis of these facts we will construct the confidence interval. So that is why slowly and gradually we are expressing these facts. Because without these facts, we are unable to construct confidence interval for the mean of normal population. Now, to construct the confidence interval for the population mean, we need to standardize this variable x bar. So we will denote the standardized variable by z. Now whatever is being standardized, so its mean would be subtracted from that variable, and the difference would be divided by the standard error or the standard deviation of that variable. We are standardizing x bar, so we will subtract the mean of x bar from x bar. So the mean of x bar is mu, so we are subtracting mu from x bar, and we will divide this difference by the standard error of x bar. As we have mentioned that the standard error of x bar is sigma over n under the root. Now, as the population is normal, so the distribution of this z would be now standard normal. Why have we transformed the variable x bar into z? Because we have a table for the possible values of the standard normal variable. So that is why we are transforming x bar into z, because we have a table of probabilities for different values of z. Probabilities are available for different values of standard normal variable. So that is why we are transforming x bar into z. That is the reason. Now, the standard normal distribution tells us that the probability that a value of z will fall in the interval from minus z alpha by 2 to plus z alpha by 2 is equal to 1 minus alpha. 1 minus alpha has already been explained in the previous lecture. 1 minus alpha is confidence level or confidence coefficient. So in the light of this statement, we can write, now from the above description, we can make a probability statement as given below. From this statement, now we are making a mathematical statement. That is, what I have done, I have just transformed this description into mathematical notations. So this is an interval. Interval is from minus z alpha by 2 to plus z alpha by 2. This is the interval, and the probability of falling the value of z into this interval is 1 minus alpha. Now, as z is equal to x bar over mu over sigma over n under the root, so we have replaced z by this and rewritten the statement. Now, what we will do, we will keep mu over here and we'll try to shift these quantities to both sides of the inequality. So now we are doing that. Next, what we will do, we will multiply this inequality by sigma over n under the root. What I have done, I have multiplied each term in this statement by sigma over n under the root. As there was no sigma over n under the root, so here is sigma over n under the root. Here was not sigma over n under the root, so here is sigma over n under the root, and similarly here is also sigma over n under the root. So now these two will get cancelled out. So next, so now this is the resulted statement. As I have mentioned that we will keep mu over here and will shift all the quantities to both sides of the inequality. So I am doing the same. Now shifting this x bar to the other sides of the inequalities. For that, what I will do, I will subtract x bar from all the terms of the inequality. Now these will get cancelled out. Next, it would be, now this can also be written as shown over here. So now we need a positive mu over here. So for that purpose, we will multiply all the terms of inequalities by minus 1. So do remember, whenever we are multiplying the inequality by a negative number, so the inequalities get reversed. What do I mean? This will become, now I have multiplied this by minus 1. So if I multiply this by minus 1, it will become plus. It will become plus. And as I have mentioned that if the inequalities is multiplied by a negative number, so the inequality will be reversed. So it has been reversed. It has become positive. It has been reversed. It was minus x bar. Over here, it became plus x bar. It was plus z alpha by 2. So it became minus z alpha by 2. So finally, this can also be written as, so this is the final statement. This is the final confidence interval for the mean of normal population. Now, what I have done, if you look at over here, this quantity is smaller than mu. So over here, this quantity is smaller than mu again. Both of them are the same notations. Over here, this is smaller than mu. So again, over here, this is again smaller than mu. Similarly, this mu is smaller than this quantity. So this mu is smaller than this quantity. So I have just rearranged the terms. Now this is the final statement of confidence interval for the mean of normal population. So in compact form, this can also be written as, now as we have mentioned in one of the lectures, we are constructing two limits. So now these are those limits. This is the lower limit, which once we represented by L theta hat, lower limit. And this is that upper limit, which once we represented by U theta hat in that lecture. So this is the lower limit and that is the upper limit. And in between these two limits, mu is expected to lie. With what? With this probability. The probability the mu is lying within these two limits is 1 minus alpha. This is the interpretation. As this is a lower limit, so this lower limit equals to x bar minus z alpha by 2 into sigma over n under the root. And this is upper limit, so this limit is equal to x bar plus z alpha by 2 into sigma over n under the root. So these are the two limits. This is the case of constructing the confidence interval for the mean of normal population. Finally, for a particular sample of size n, 100 into 1 minus alpha % confidence interval for mu is given by x bar, this small x bar, plus minus z alpha by 2 into sigma over n under the root. So now for the construction of confidence interval about the mean of the normal population, we need to remember only this expression. Not all those derivations are, and not all those steps which we have done for the derivation of this statement. What do we need? We need only this statement. If someone remembers this statement, so he is capable of constructing the confidence interval for the mean of normal population. So all these steps have been taken for the derivation of this statement. All these steps have been taken only to derive this statement. So this is the final statement, and we will use this statement for the construction of confidence interval for the mean of normal population. For the mean of other population, we can also use similar statement but with a bit modification. So it was all about the derivation of confidence interval for the mean of normal population. Hope this will help you in the construction of confidence interval for the mean of normal population. Thank you for watching the video.